I'll introduce my company a little bit first, and then we'll bring up a panel of students, which is always a fun thing to do. So, like you said, we're Sistema Technologies. We're a local company. We work in aerospace and defense. Our space mechanisms groups are growing quickly. We're AS9100 certified company. We have a broad spectrum of capabilities that we do. A lot of it centers around mechanisms. A lot of those mechanisms are pyrotechnically driven, so cartridge actuated devices, pads. We also do full range of environmental testing, vibration, thermal chambers, shock, and other things. We have a wide range of technologies that span defense and space systems that folks here might be interested in coming and talking to us about in the Sponsors Lounge when we get a chance to do that. These are the ones there. Some of them that you might highlight include propulsion systems such as pyrovalves and advanced green monopropellant propulsion systems. Other things like parachute motors, stage separation, booster separation, and those types of mechanisms. We've been around for a little while, worked with a lot of the aerospace companies and primes. The Small Business Administration has recognized our work, as well as working on the Orion space capsule for the Lockheed Space and NASA. And our testing services have a broad spectrum, which include not only standard environmental testing equipment that you see there, but also functional tests. So if you have some special kind of tests that you need, some special kind of an operating condition or want to function your equipment, and we can set that up for you and help you get the data and help you find a place to run the test. That includes flight testing with sounding rockets, aircraft, rocket sleds. We've tested on a variety of platforms. And so the topic of today was finding your next engineer. Part of the things that we have in this industry that we all talk about when we get together in these conferences is how hard it is sometimes to find the right people who fit into the niche environment that we have in this industry. That involves, not only the STEM education that we hear so much about, but for a small company like ourselves, it also involves being able to work a project from concept to production and being able to have hands-on capabilities to go down in the R&D labs or to go into the production floor, to go out in the test lab and take data. And that's a really challenging set of skills to put together in an employee to bring them on so you can grow into our new space industry. One place we've been successful with that is internships and bringing students in from the University of Washington, amongst other fine and learning institutions. So today we brought up a panel of these students from the Advanced Rocket Propulsion team at the University of Washington. It's not only a team, but it's a capstone design project for course credit. And in this, they'll be able to show you the things that they learn above and beyond what we might consider standard classroom work. So, panel. Come.
Is that for me?
It's for you.
Oh,
because you're introducing the team, right?
Oh.
Sit down, so I get a chair.
Sure, I just have one. Okay. Hi, I'm Kendall. I'm the Chief Engineer for SARP, the Society for Advanced Rocket Propulsion. And before we open up the panel, we'll just do a quick briefing on what we are, what we do. We're a group of 30 to 40 undergraduate students from all classes. We design, build, test, and launch a custom hybrid rocket to 25,000 feet. We have 4 technical sub-teams: propulsion, structure, recovery, and payload. And it's my job as chief engineer. I act as a principal integrator for all the teams to make sure that we have one fully functional vehicle at time of launch. Everything is totally student designed and manufactured, from the hybrid propulsion system to the composite airframe and even the recovery parachutes. We launch 3 payloads, one of which includes a K through 12 outreach payload. But with that, I'll lead you to Daniel, talk to you about our electrolysis payload.
Hi, I'm Daniel Cruz, a recent graduate of University of Washington. So this year we included an innovative electrolysis experiment as our payload that's brand new to our SARP program. So our design challenge for ourselves was to create an experiment to miniaturize and apply to CubeSats water electrolysis technology. Electrolyzers are devices which split water into hydrogen and oxygen gases, which have advantages for space hardware ranging from life support to in situ rocket propellant production. Further, we challenged ourselves to integrate the experiment into the SARP rocket, and ultimately to test the system in the microgravity environment of Blue Origin's New Shepard vehicle. So on the right of this slide here, you'll see our off-the-shelf electrolyzer unit. You can see the serpentine flow field where the electrolytic reaction occurs. On the side, you're seeing hydrogen gas exits the device, and on the opposite side, oxygen exits. So this is a broad system-level overview of the package we designed. We had to equip the electrolyzer with power, control, and instrumentation systems, as well as to manage the fluids within the unit. All of the auxiliary systems here were designed from the ground up throughout the course of our program. So this is a schematic of our fluid management system. You'll see the electrolyzer there. Prior to flight operations, the electrolyzer is loaded with about 1 milliliter of water. Service valves are used to fill the gas collection lines with a blanket gas, which serves as a back pressurant as well as facilitates our post-recovery analysis to verify gas collection. A mixture of water and the product gases, hydrogen and oxygen, hydrogen through one line and oxygen through the other, exits the electrolyzer. To passively separate these two phases, the water and the gas, without relying on buoyancy, we pass the mixture through our liquid vapor separators. Each gas is then stored within a sample bottle for further analysis. The primary diagnostic here is pressure, which is used to extrapolate the electrolyzer's performance when considered together with the power characteristics of the device. So on the lower left here, you'll see the prototype of our liquid vapor separator system. Some less than expected performance of our prototype led to the development of the design that you'll see here. So essentially, we have a reservoir filled with steel wool. This presents a high surface area so that when the water enters the device, it is entrained by surface tension forces within the steel wool, and a hydrophobic membrane allows the gas to percolate out of the unit. So here on the left is a transparent view, and on the right an exploded view of our 2U CubeSat package. It was a major challenge for our team to integrate our system into this geometric constraint given the high number of components. This was done using CAD software. A key feature of what you're seeing here is the use of molds on those walls to restrain our components within the unit. And this is a prototype whose purpose was to perform system checks while flying with the payload package of the SARP rocket. You can see one of the gas collection bottles and one of the pressure transducers there within one of the 3D printed molds. And on the right is the unit integrated into the rocket for one of the test flights. The full system is presently being prepared for our ultimate objective of flying on Blue Origin's New Shepard vehicle. So with that, I'll hand it off to Ryan to talk about our propulsion system.
Hi everyone, my name is Ryan Fowler. I am a recent graduate of the University of Washington Aeronautics and Astronautics program, and I was a senior member of the propulsion sub-team on the SARP team this past year. And today we're talking to you about our hybrid propulsion system. So what you can see on the right is our fully assembled rocket on the launch rail with the fill lines attached, as our team is preparing it for a test launch. Now, as Kendall said, the goal of each test launch was to send the rocket to a 7-kilometer AGL altitude, and to do that, we designed a Class O hybrid motor. Getting into the specifics of the design, at the beginning of the year, we used software such as NASA CEA and OpenRocket to determine the performance characteristics our rocket would need in order to achieve our goal. Those characteristics then led our design to this final product. On the left is our aluminum oxidizer tank, which is directly connected to our aluminum shell combustion chamber, and also in work this year has been an actuated valve that would sit between them in order to keep them separate. Getting into the oxidizer tank, it is entirely made of aluminum. It is designed to hold 27 pounds of liquid nitrous oxide, and it has been hydrostatically tested to 50% above the critical pressure of nitrous, so it is very safe. At the base of the oxidizer tank is our injector plate. It has 11 orifices in a showerhead design, and seated directly next to the injector is our polycarbonate diaphragm and igniter assembly. Now, upon ignition, an incendiary charge on the diaphragm ignites, which both vaporizes the top of the fuel grain and weakens the diaphragm to bursting. And when that happens, the nitrous oxide in the oxidizer tank is allowed to flow into the combustion chamber and ignite the motor. And the picture on the bottom right is a view of the bottom of the oxidizer tank after a burn has occurred. So the combustion chamber, it is a 5-inch diameter aluminum shell, which houses our paraffin wax and asphalt emulsion fuel grain, along with our 3 linen phenolic liners, our pre-combustor, our post-combustor, and our outer liner, which this year has been changed to span the length of the combustion chamber in order to eliminate any unwanted gas paths. And at the base of the combustion chamber is our graphite nozzle. Now, in past years, the nozzle was made entirely of graphite, but this year we modified it by replacing the end of the diverging section with aluminum in order to make it more structurally stable. Now, with this propulsion system, this year we were able to perform 6 full-scale static tests. These tests were designed to measure the thrust of the motor along with the pressures and temperatures in the tanks, and those data values were then used to determine the mass flow rate and total impulse of the motor itself. And with all of these tests, our primary goals were to validate our theoretical models using the data we gathered, validate our ignition reliability, and validate the integrity of the combustors that we were using. And our secondary objectives were to develop procedures for handling the nitrous safely, assembling the motor correctly and reliably, and teaching our team members about safe field operations. And this is the data we got from our final test. On the left, you can see our thrust curve in yellow, along with the pressure data we got from the oxidizer tank in blue and the combustion chamber in red. This test was performed using 12 kilograms of nitrous oxide, and it gave us a peak thrust of 2.2 kilonewtons. And as the test lasted, the burn lasted approximately 12 seconds, that gave us a total impulse of approximately 18 kilonewton seconds, which is very close to Class L motor classification. Through all this testing, though, we learned some very important lessons. We learned that our motor ignition is not always consistent due to some igniters being weaker than others. We learned that accidental chilling of our pre-combustor prior to burning can lead to burn-throughs of the combustion chamber shell, as you can see in the pictures below. The burn-through on the left occurred during our first test, and the burn-through on the right occurred during our 4th test. And getting into our data analysis, we learned that we were not achieving the chamber pressure and thrust we needed due to both our graphite nozzle being oversized in the throat and due to the low temperature of the test conditions, actually lowering our mass flow rate of the nitrous. And these are some hard lessons to learn, but we actually now we have plans in place for coming years in order to mitigate all of these issues. And now I'll hand it back to Kendall to talk about the aerodynamics and structures.
So this year, SARP performed wind tunnel testing at the Kirsten Wind Tunnel on the University of Washington campus. And the goal was to determine the fin geometry that yielded the most stable aerodynamic profile. So we were going for least response to changes in inclination angle. So we swept through multiple inclination angles in the wind tunnel test. The model was designed on a 1/3 scale of the full rocket and was designed for modular model changes to allow for changes in length as well as easy change of fin geometry. The composite airframe is designed with pre-impregnated carbon fiber laid up around an aluminum mandrel and cured in an autoclave, and all of this happens in a composites lab on campus. The upper body tube is 10-ply cylindrical, and the lower body tube is also 10-ply cylindrical, but we also have aluminum hex core fins with carbon fiber face sheets as well as tip-to-tip layups that are cured in an all-in-one with 3 external molds for structural stability. Our recovery coupler sits above the oxidizer tank and below the upper body tube, and it serves as the hub for all of our recovery operations. It also houses the oxidizer fill and vent mechanisms. Because it serves as the hard point for the entire recovery system, we decided to make it out of aluminum this year with an aluminum welded bulkhead for increased structural strength. The recovery system is housed inside the upper body tube. It's fully student designed and manufactured parachutes as well. So we have a single separation dual deployment system. So as you can see in the figure, the center figure is our single separation of the nose cone, which pulls out the drogue parachuted apogee. And then a SARP team member developed component, which we'll see on the next slide, the parachute stage separator. At 1,500 feet, AGL releases the drogue parachute to pull out the main parachute. So the figure on the left, as you can see, is that's the recovery coupler with the implementation of the recovery avionics package. And on the right is the recovery avionics package. So the Peregrine Raptor canisters, they pressurize the upper body tube, separating the nose cone and deploying the drogue parachute apogee. And then the parachute stage separator, both of these components are controlled by the 2 Raven altimeters. The parachute stage separator releases a drogue parachute, which can then deploy the main. We do sufficient component and system level testing So you can see the figure on the left is our component level of the avionics package. And then the center is a full system level test of the package. And then on the right is assembly right before test launch. So we do component level and system level testing to ensure a reliable recovery system at time of launch. So.
Hang on that for a second.
Okay.
I got this one over here. So that's a quick overview of what they do on the team, and that you can see the hands-on, you can see the design work, you can see the analytical work. You can see some interaction too with us in industry where we get a chance to support them, how they build their structures. So that's pretty interesting. So now we have some time left specifically so that people will come and ask questions. I have a quick one because we at Sistema are often involved in pyrotechnics. I'm interested in the igniter. So
Yes.
Could you go into some more detail on exactly what you use for the igniter, and then how did you what was the mode of ignition that you expected it to perform?
Okay, so the igniter is a homemade mixture of, there are 2 nuggets of rocket candy that are covered in flash powder. The rocket candy is designed to have a slow burn through the diaphragm itself. All the flash powder is kind of a quick a flash in order to vaporize the fuel grain.
Okay, so
Yeah.
vaporizing the fuel grain, so it was a temperature pressure kind of an event? Okay.
Yeah, it's all done in-house. Like we just, we cook it and on campus, and we just basically super glue the mixture onto the diaphragm.
You do some component testing in that where you flash the power?
Oh yes, for every single burn test, we had an igniter test where we brought 2 igniters to every test, and before every burn, we would just test the igniter.
Okay, excellent.
Yeah.
Excellent. Anybody else? We have some microphones up here. Here we go. I see somebody come. You got a question? Oh, here we go. You first.
All right, so I'm from Arizona State University, and I'm blown away by what you guys are doing. We let other people do rocketry stuff. We have clubs that aspire to what you're doing, which is outstanding. So hopefully we can take some notes. But what I'm very interested in is I'm a project manager for a VR lab at ASU, and we're working with entirely undergrads, and they're so excited. How do you whip those kids into productivity mode? So when it comes to actually juggling 15, 18 credits, these kids are incredibly talented. It's just, what is the best form of project management in a university setting?
I think that's a chief engineer question. That's a chief engineer.
But I'm just saying ASU is incredible and might beat you at other things, just we're all good.
Well, thank you. We're proud of SARP and what we do. So we actually, it's like herding cats. As you know, we're all undergrads. And that's the nice thing about having it involved in the curriculum. So I've been involved in the program for 3 years, and we've gone from 9 people to 30 to 40. And to have it integrated into academia it's invaluable. But we went with the new organization structure this year, and we had sub-teams, the 4 sub-teams I mentioned, and then those sub-teams had sub-teams. So like, for instance, the structures sub-team had someone in charge of the airframe and then someone else in charge of couplers and hard points. And we also had myself as chief engineer, and then we also have Alex here, who's project manager. So we split so I had the design oversight and technical integration part of it, and he had all of the behind-the-scenes logistics, making sure everything worked. And that worked very well for us. We were able to accomplish a lot more. And then as far as getting the undergrads whipping them into shape, what we actually think we're going to implement next year, because we had a team that was so big and we have only 1 vehicle that we work on, we're going to split it up into 2 projects ideally. So we'd like to have 2 rockets, one for teams that's a little bit less technically involved, that they can develop their own rocketry knowledge base, maybe whether it be a subscale solid motor or something else. But that's something that we like to implement, so that the undergrads that maybe haven't had this integrated into their curriculum yet, they can learn alongside us and then be more prepared for the advanced task of a hybrid motor.
Thank you.
Yeah.
Excellent. Thank you. Next. Thank you.
So I'm a student at Virginia Tech, and we are pursuing a lot of efforts there to try to get individuals into this kind of work that would not necessarily have found themselves there to begin with. A lot of the non-engineering crowd put an A in STEAM, all that kind of stuff. So I just wanted to kind of pick your all's brains to see, is there a role that you all see for people with these different skill sets to apply to a project like this? And if there is that role, how can you maximize their efforts in that and get people excited about rocketry when they've never thought about doing it before?
Well, there are competitions that you can enter into. I think it's really important to have a challenge, a very specific challenge for people to work towards, so that then they can do the research on, okay, so I don't know anything about rockets, but I've been told I need to make a rocket. So, then they'll go and they'll read about it, and as long as the passion is there to meet the challenge, then a passion for rocketry might grow. I guess that's how I might answer that.
Well, I'd say certainly from industry, when you get out there and you start working on these things in industry, there's a lot more roles that are involved than just the technical. And so I think that I've seen it from dealing with the students on how they bring those things in-house. I think that would be interesting to see if some of the other schools inside the university would be interested in supporting some of those endeavors. And that could be other hard sciences that aren't quite in engineering. It could be media, like we're doing here today. And there's a number of things, I think. Here we go. Yes, sir.
You talked about your electrolysis experiment is going to go on the sounding rocket as well as on New Shepard. Could you talk a little bit about the design differences between designing the same experiment for both platforms, and which New Shepard is it going to be on?
Okay, those are great questions. So it was challenging because the New Shepard payload box is not as restrictive as a slender rocket body tube. So we mostly made it so that the system is fairly modular, and that although we have it crammed all into this tiny box for the sounding rocket, it can be broken out and installed into the payload box for New Shepard. And which flight? Well, we're going to be integrating it into the payload box in the autumn, so whenever they're ready. Yeah.
Yes, sir.
Okay. Yes, hi. My name is John Hunefeld. I'm the pillar book guy. I've got the model back in the corner. And in prototyping that, I did a lot of 3D printing, and I'm a big advocate of it. I think it's great for prototyping, and I'm wondering, have you looked at, looking at your structures, I was thinking it looked like a great application for some more additive manufacturing. Have you looked at using that in your rockets?
Well, actually, our nose cone was entirely 3D printed, along with the, was it the PCB as well? Or was that?
So we had our nose cone was printed in multiple parts. We have Melanie here who designed it. She can talk about that a little more if you want. We also did a lot of additive manufacturing for the integration of our nose cone and our payload housing for the SARP payload itself.
Okay.
And then we did 3D printing for the recovery bay. There were some 3D printed bulkheads. On the slide there was a piece that had a rocket on it, looked like a SARP logo. That was 3D printed, and that housed all of our avionics, and that actually kind of sandwiched the upper bulkhead on the recovery coupler. So we utilized it a lot in our payload and recovery.
Okay, great. Thanks.
Here's your opportunity. Open mic. I have one more question. So requirements. That's what in the industry, right? That's what drives my daily thing is what are my requirements from my customer, what are the requirements of the system. So this is kind of a self-driven project. How do you develop your requirements, and how do you flow them down to your subgroups then to ensure that everything fits when you do final assembly, that it physically fits, it functions as advertised? Go ahead.
Well, so we had the overall goal of getting a rocket to 25,000 feet. And then, like I said, with our initial design, we had the performance we had to adhere to in order to achieve that goal. And then, as the chief integrator, was kind of hovering between all the sub-teams like my propulsion team and the payload teams, was making sure that as each component was made, it was going to be able to fit with the overall goal. So the design itself took a lot from previous year's designs, in terms of like modifying those and making them better. So we had a decent idea of what it was going to look like, but the entire inside has been ours to play around with. Like I said, we would change a few things with the propulsion system. The payload has been entirely reintegrated. And so there's been a lot of variation to a rocket that has been a pretty storied past in the past few years.
Just to add on to that, for the last few years, we've been designing for the Intercollegiate Rocket Engineering Competition, which has it has altitude goals to reach, also has manufacturing requirements, so like manufacturing your own fuel grain, manufacturing your own parachutes, as well as we have like safety requirements like redundant recovery systems, stuff like that. So those are the hard base requirements that we have, and then like Ryan said, the insides are kind of ours to toy with, as long as they meet those requirements.
Question? Oh, come on. Okay, well, I think maybe there's time for one more, so I'll ask the big one. It's the total lead in at the end of this. How does this get paid for? Right?
So Sistema is one of our sponsors. They've been really helpful.
And we're not the only ones here. I mean, there's a lot of our sponsors here in the audience today, but if I got a couple of minutes left, I'm going to use them up, right?
So we have many sponsors. Sistema is one of our sponsors. They've been generous and helped us out the last several years. The Department of Aeronautics and Astronautics, Blue Origin, obviously, flying our payload, Spaceflight, I believe, Aerojet Rocketdyne. It's a big sponsor. So we have a lot of corporate sponsors. We also do crowdfunding. Thanks, Mom and Dad, families. They help out with this too. It's a big family effort from corporations to neighborhoods.
And also with this year, it becoming a capstone project. Like Kendall said, we had a lot more funding from the area department this year, both in terms of the payload and just as being a major capstone project with a lot of students involved. We naturally got a lot more funding for that, which was very helpful, and freed up a lot of space for us to just really work with the rocket.
Excellent, thank you. And I'll wrap with the words of saying, we have personal experience in bringing some of these students on board as engineers, bringing them on as interns, and our experiences with that has been very good. In fact, one of our best young engineers who was part of the internship program, sitting out here in the audience today, and we've had great success. I currently have an intern. He's not AA, I'm sorry, he's from my department of mechanical engineering. But it's a great way to incorporate that talent into your corporate culture. It's a great way to reach out to the universities as well and find these candidates, and it's a great way these types of teams and capstone projects are ways to find the teammates that you need with the specific skills that you need to bring them on to your team, your corporate team. So I encourage each and every one of you to find out more about this particular team and how to support them or how to bring those students in, but also to find other capstone projects that exist at the University of Washington and other fine institutions here in the state of Washington. So with that, I'll leave you to the next panel. And our testing services have a broad spectrum, which include not only standard environmental testing equipment that you see there, but also functional tests. So if you have some special kind of tests that you need, some special kind of an operating condition or want to function your equipment, and we can set that up for you and help you get the data and help you find a place to run the test. That includes flight testing with sounding rockets, aircraft, rocket sleds. We've tested on a variety of platforms. And so the topic of today was finding your next engineer. Part of the things that we have in this industry that we all talk about when we get together in these conferences is how hard it is sometimes to find the right people. I'll introduce my company a little bit first. And then we'll bring up a panel of students, which is always a fun thing to do. So like you said, we're Sistema Technologies. We're a local company. We work in aerospace and defense. Our space mechanisms groups are growing quickly. We're AS9100 certified company. We have a broad spectrum of capabilities that we do. A lot of it centers around mechanisms. A lot of those mechanisms are pyrotechnically driven, so cartridge actuated devices, pads. We also do full range of environmental testing, vibration, thermal chambers, shock, and other things. We have a panel of these students from the Advanced Rocket Propulsion team at the University of Washington. It's not only a team, but it's a capstone design project for course credit. And in this, they'll be able to show you the things that they learn above and beyond what we might consider standard classroom work. So, panel. Come.
Is that for me?
It's for you.
Oh,
Because you're introducing the team, right? Get down, scoot down, so I get a chance. Fit into the niche environment that we have in this industry that involves, not only the STEM education that we hear so much about, but for a small company like ourselves, it also involves being able to work a project from concept to production and being able to have hands-on capabilities to go down in the R&D labs or to go into the production floor, to go out in the test lab and take data. And that's a really challenging set of skills to put together in an employee, to bring them on so you can grow into our new space industry. One place we've been successful with that is internships and bringing students in from the University of Washington, amongst other fine learning institutions. So today we brought up a wide range of technologies that span defense and space systems that folks here might be interested in coming and talking to us about in the Sponsors Lounge when we get a chance to do that. These are the ones there. Some of them that you might highlight include propulsion systems such as pyrovalves and advanced green monopropellant propulsion systems. Other things like parachute motors, stage separation, booster separation, and those types of mechanisms. We've been around for a little while, worked with a lot of the aerospace companies and primes. The Small Business Administration has recognized our work, as well as working on the Orion space capsule for the Lockheed Space and NASA.